All right, let me get started. First of all, Urmi and Grace, thank you so much for arranging this. It's certainly be a pleasure to be here and an honor to give this presentation. As Urmi mentioned, my name is Madhavan Swaminathan. I'm with Georgia Tech. I've been here now for 26 years. And I also serve as the director of the 3D Systems Packaging Research Center. Some of you probably know of the previous director of PRC, Professor Rao Tumala, very well known all over the world. He retired a couple of years back and I took over from him. So I've been involved with iNEMI now for some time, and I've been part of this iNEMI task force on 5G millimeter wave. So I thought today's presentation can focus on millimeter wave communications in general, but more importantly, packaging for millimeter wave communications. So I'm located in Atlanta here. It's a beautiful day outside, and I hope the weather is great at your end of the world as well. So with that, let me get started. So as an outline, I'm just going to use a single slide to introduce PRC. And then most of the presentation is going to be focused on millimeter wave package integration. And then I'll touch on some of the work that we are doing in the area of millimeter wave design by making use of some new machine learning concepts, and very briefly talk about the path forward, some of the other work going on at PRC, and then try to summarize. So the Packaging Research Center used to be started as an NSF Engineering Research Center many years back. We are now in the 27th year. And NSF typically funds you for 12 years. After that, since then, we've been self-sufficient. And we do a lot of work in the area of advanced packaging. So that's the research part. There is also an educational aspect to it, where we offer a lot of courses. And we also spend a humongous amount of time in workforce development. So all of our work is centered around advanced packaging as it relates to systems integration. So we are a holistic center, so we don't focus on just a single aspect of packaging. We cover design, materials, process, assembly, reliability, thermal, as well as system integration. The center team consists of 29 faculty from 5 schools indicated here. So it's a highly multidisciplinary center, full-time research staff, more than around 50 students that are supported. And we also have visiting engineers on campus from the various companies that we work with. So the companies that we interact with is shown here, more than 40 of them, 14 universities. We also work very closely with SRC, DARPA, Department of Defense, NSF, and more importantly, iNEMI. And we've been members of iNEMI now for many years. So with that, let me get started and get into wireless communication. So I'm sure all of us have followed these various generations of wireless communication all the way from 1G to 4G. And what is coming now is 5G, and if you go beyond, it's 6G and so on and so forth. So if you look at the primary driver over here, it all relates to the data rate. How much of data can you actually transmit and receive through these wireless communication channels? And if you look at a lot of the emerging applications that are coming up in the area of augmented reliability, virtual reality, and so on and so forth, you realize that you need a huge amount of capacity to support it. And that is where you have around 20 gigabits per second that is being promised through 5G, close to around 1 terabit per second once you get to 6G and so on and so forth. So just to put things in perspective, with a speed of around 20 gigabits per second, that translates to downloading 2 to 3 of these high definition movies in roughly a second or so. So clearly this capacity is very important. But there is also another issue that we call as pervasive connectivity, where if you look at the density of devices that you need to sort of connect to each other, It's mind-boggling, all the way to 1 million devices per kilometer squared for 5G, going up to 10 million devices per kilometer squared for 6G. And you also want to have unmanned mobility, because right now with all of these 5G, you're looking at fixed point networks. You want to make sure that there is, a lot of these machines begin to talk to each other with very high reliability and low latency. So you can think of this autonomous transportation. And ultimately, intelligent communications with artificial intelligence coming into the mix. There's a lot one can do from a wireless communication standpoint when it comes to intelligence. So if you look at the spectrum of frequencies that we are trying to go after between 5G and 6G, you get into the millimeter wave. And what is very important over here, along with everything that is listed, is energy efficiency and also being able to bring that intelligence as part of your communication. One of the biggest challenges that we have as we get into higher frequencies is path loss. And this is very well known in wireless communication. So if you look at the spectrum here, going up to 6 gigahertz, that is your sub 6 gigahertz 5G, the path loss tends to be a whole lot lower as you get into these millimeter waves in the 30 to 300 gigahertz range. Because if you look at this figure here, within around 100-meter distance, as you go higher up in frequency, the attenuation tends to get very, very high. So you have path loss related issues, and it becomes even higher as you get into the terahertz frequencies, and even when you get into visible light and so on and so forth. And one of the problems that we have along with this path loss is this atmospheric absorption. So if you look at this graph over here, you see these peaks, and those are specific frequencies where, because of the atmospheric conditions, you essentially have very high levels of attenuation. And this is part of the reason why even with 5G kinds of solutions, you have these circles shown over here where you can operate either in the sub 6 gigahertz range or the millimeter wave range. And as you can see, as you get into the millimeter wave range, the region over which you can actually transmit and receive information tends to reduce. So in this presentation, I'm going to focus primarily on millimeter waves that covers the frequency range from 30 gigahertz to 300 gigahertz. And with this kind of a path loss and absorption loss, you need to somehow compensate for this using your antenna and RF circuitry. So that brings us to the links and what we call as the link budgets. So this could be the backhaul link as shown over here, or it could even be the access point requirements indicated here. So what I've done is put some numbers in based on some calculations. So let us say that you have two towers over here that are separated by a distance of around 100 meters. And based on the previous slide, the path loss is roughly around 133 dB at a frequency. I just picked a frequency in D band of 140 gigahertz. So let's look at how the link actually operates. You're starting with a transmit radio, and it has some power level associated with it, and it goes through the package. So you have some loss that you incur, and then you have an antenna that has a certain gain. So you put these three together, you get this EIRP of roughly around 71 dBm in this particular example. And you're transmitting over a distance of around 100 meters. So by the time the signal reaches the receive side, you have diminished that signal power quite a bit. So you are trying to enhance that power through that antenna gain. And then once again, you're going through these package losses. And depending on the amount of signal to noise ratio or a signal interference noise ratio that you want of roughly 30 dB, you allow for a certain noise figure for your RX radio. And this is an example with, let's say, 128 ohm. Now, clearly, if you see over here, if you look at some of these budgets, these are fairly hard to meet, especially when you get into the millimeter wave frequency region. And in today's presentation, there are three elements that are very, very important here. One is the antenna itself. The second is the package. And the third is that radio, because what happens is the efficiency of these radios are not very good. As you get into higher frequencies, they tend to generate a huge amount of heat that you somehow need to address through packaging. So the key takeaway is that you need to construct this heterogeneous integration platform using advanced packaging, and that becomes a key enabler. So let's look at IC technologies. So this is a very interesting graph where the x-axis is your frequency and your y-axis has two parameters associated with it. One is half a lambda and the other is the square root of the area, basically of your chip, your transceiver chip. So half a lambda is typically the size of the antenna element that we use, and that is this blue line shown over here. So as you go higher up in frequency, the size of those antenna elements tends to go down. And all of those circles that you see here are several implementations available in the open literature where people have built these transmitters or transceiver chips. So I'm going to take this crossover point here at roughly between around 70 to 100 gigahertz. And you'll notice that to the left of it, because you're operating at a lower frequency, these antenna elements tend to be fairly large. And the only way to integrate these antennas is by integrating them in the package. But then you move to the right-hand side, you'll notice that the power efficiencies or the amount of power output from these chips are not very high. So most of the die size is consumed by the transceiver itself. And therefore, once again, you have to integrate your antennas in the package. So the key message moving forward for millimeter wave communications is that antenna and package is a necessary technology. So with that, let's look at what are the options. And I'm going to put this in the context of advanced packaging and heterogeneous integration. So if you look at state of the art in terms of these architectures, there are two ways by which you can do it. One is 2D, the other is 3D. In 2D, you can use different ways of doing this. One is a silicon-based approach, what we call as a silicon interposer. The second could be an organic-based approach. This is a very, very popular approach for RF types of solutions. The third is a glass-based approach. I'm going to come to this shortly. And of course, there are others like LTCC that has been around for a long time. You can also make use of silicon micro machining and so on and so forth. On the 3D side, you can try to stack these chips on top of each other using through silicon vias or TSVs. This is more of an IC foundry based process, or you can come up with a non-TSV based solution. And if you look at what is shown here using glass based solutions and these non-TSV based solutions, that is what we have been focusing on at the PRC now for a few years. And that is really what I'm going to be touching on as part of this presentation, along with comparison with everything else that is out there. So let's look at the platform itself. Now, if I look at these three different materials I can make use of, silicon, organic, and glass, and try to compare those material properties with each other, that is captured on this slide over here. And the key takeaway here is that you want to have materials with silicon-like properties that maximize the chip and board level reliability and support larger body sizes. So what do I mean by that? Now realize that you want to be able to work with an interposer that is as stiff as possible, especially if you're trying to go after rigid types of applications. Now, in addition to that, you're trying to assemble the chip onto this interposer and the interposer onto the printed wiring board. So you want to make sure that the fatigue life in terms of the number of cycles maximizes the chip level fatigue life as well as the board level fatigue life. And that requires that you stay in a certain range in terms of the coefficient of thermal expansion of the material sets you actually use. And that is where the 7 to 9 ppm per degree centigrade comes in. In addition to that, you want very low surface roughness. Young's modulus is where the stiffness part becomes very important. And if hermeticity is important, then you want zero moisture absorption. In addition to that, if you look at silicon interposer based solutions, since it's an IC foundry based process, you're limited in terms of the reticle size, 35 millimeters on a side, and moving forward, you probably need much larger body sizes as indicated over here. And we believe that glass interposer is a very, very good candidate. So let me now get into antenna and package. Now we've all heard about massive MIMO. Okay, so with massive MIMO, you want to be able to build very large antenna arrays, and these antenna arrays need to have very high gain antenna elements. And when you build these antenna arrays, you also need to provide for a full field of view as indicated here. So let's say you have a transmit array here, you have several receivers, and you want to make sure that you're able to cover this entire region as indicated in this figure. Now, when you look at these kinds of solutions, beamforming technology becomes a very, very critical part of the overall solution that you go after. And there are three fundamental ways by which you can do that. One is completely analog. The second is digital, as indicated here, where you're generating the beam and doing beam steering using digital solutions, okay, or digital ICs. And the third is a hybrid solution where not only are you doing this beamforming using your digital ICs, you're also making use of phase shifters here to be able to create your beam and then steer your beam. And we all know that when it comes to beamforming, you want to be able to create a laser type of a beam, a pencil beam that is able to be directed at specific regions. One embodiment of an antenna array is indicated here, and this is a 384 element W-band phased array. This was done by Nokia. And one of the things you will notice here is that you're making use of huge number of elements to be able to get enough gain out of this antenna. In addition to that, the solution that is being pursued is a modular solution. So you work with a subarray and then you build this overall antenna array by making use of the subarray. And this gives you various opportunities in terms of how you want to implement this array. So you can make use of maybe spatial multiplexing if you like, or you can try to make use of this entire antenna array to maximize your gain along a specific direction. So with that, let's get into what are some of the requirements. And I'm going to put it in the context of glass-based packaging. So what you want to construct, let's say on the transmit side, is an antenna array solution where the array is on the top side, so you're radiating out this way. And then beneath that, you have layers of wiring, and the layers of wiring contains different kinds of passive components such as filters, couplers, and so on and so forth. And beneath that, you have the chips, the ICs. And the whole idea here by creating a construction like this is to ensure that you're able to reduce the amount of loss that you incur when you go from the ICs to the antenna array on the top side. So,
Professor, we seem to have lost your slides. I think you're projecting something from your email. Yes. So if you
is that right? Okay, let me.
Yeah, readjust your display, please. Thank you.
Let me come out of this. I'm sorry. Do you see this? Do you see it now?
Yes, we do. If you can go back into slideshow when you're ready. Thank you.
Okay, very good. Thank you.
Great. Thank you.
Okay. So what you want to do here is to reduce that loss going from the IC to those antenna elements. And the only way to do that is by reducing the thickness of the module itself. And that requires that you work with very fine lines and spaces and try and reduce the number of layers you actually make use of. So with glass-based packaging, so I'm going to introduce both chip last and chip first approach. And what we do is we make use of these high frequency polymer materials, both dry and liquid films that have low decay and DF associated with that, to be able to build the redistribution layers or the passives on either side of the glass substrate. And we also make use of glass to build these very advanced waveguides and also use the glass for chip embedding. Now, the nice thing about glass-based packaging is that you can make it double-sided and you can integrate components in it. And as I mentioned earlier, the electronics is beneath the antenna to reduce the form factor and loss. And I'm going to touch on thermal management later on, where the heat is now removed from the backside of the chip. And one of the nice things is because you have this variable CT associated with that glass substrate, you can try and assemble it directly onto the printed circuit board and at the same time maximize both the chip level reliability as well as the second level reliability indicated here. So let me start with this hybrid beamforming transmit TX antenna array. And this is something we are trying to do with glass. So the concept is the following, similar to what I showed you earlier. So you try to make use of a modular approach where a single module here or a subarray consists of a 2x2 patch antenna array where you have phase shifters embedded beneath it and the chip embedded beneath that. So that is what is indicated over here. So you have the beamformer, the power amplifier, the switches, the phase shifters, and above that, the patch here. And then we put these patches together to be able to build your entire antenna array. So for example, to build a 256 antenna element using 64 subarrays, you get a gain of around 28 dB or so. And the interesting thing about this is that you construct these 8 basic beams over here with this 2D array, where you're relying on the phase shifters to get this fine scan, and you're relying on this beamformers to be able to get you this larger scan as you try to cover the entire field of view. And you can increase the number of subarrays that you make use of. So for example, you can work with 64 by 32 elements. That translates to a 32 by 16 subarray, gets you a gain of around 36 dBi. Now the key message over here is that as you go up in frequency, you have to work with larger number of antenna elements to get the gain that you're looking for. In this particular case, we are operating in D band, which is at 140 gigahertz. So with that, let me give you some results that we have been able to come up with so far. So this is an example where we were trying to build these polymer layers on either side of glass to build antennas. And this is an example of an antenna 4x4 patch antenna array that we were able to design and fabricate. And you notice the results here. This was in D band, which is at around 140 gigahertz or so. And you get fairly good bandwidth if you look at it from an S11 standpoint, return loss standpoint. And you get a gain of around 16 dBi with these number of elements. And remember, you can actually build a much larger array with this. And this table shows a comparison with what has been done using other materials like LTCC, PTFE, LCP, and so on and so forth. And you see these results are actually quite good with these glass-based solutions. Now, let me switch a little bit to the receive side. So we've worked with antenna solutions over here as well. Once again, the substrated glass with polymer layers on either side. So here we were making use of a different polymer. And the nice thing about this solution is that, all of us are familiar with these Yagi arrays. And if you look at Yagi arrays, they make use of a dipole element. In this particular case, we have been able to create these Yagi elements using monopoles. And what that allows you to do is that you can have a single-ended feed over here. So this is your radiator. This is your director. So the beam is directed this way. And this becomes your reflector. So your ground plane is your reflector, is a coplanar waveguide CPW kind of a solution. And you see with this 1x2 array, we get a gain of around 10 dBi, between 8 to 10 dBi or so, covers a frequency range of between around 24 to 40 gigahertz. And you see the antenna pattern here as well. So with these linear arrays, there's a lot of comparison that we have done here, showing that the kinds of solutions we have been able to develop using this glass-based solution is actually quite good compared to what has been published out there. And we've extended this concept to much higher frequencies. So if you go to, let's say, 140 gigahertz with a 1x4 array, we get a gain of around 10 dBi or so. Obviously, this design here is slightly modified compared to the design that I showed you earlier on at lower frequencies. And the whole point here is this goes into the receive side. It goes over here, and we can certainly increase that gain by bumping up the number of array elements. Now, when you try to work with antenna arrays, right, you need power dividers. This becomes very important. So this is an example of these Yagi antenna arrays. These are the dipoles, and where we've made use of a balun here. And these elements here, these feed elements, represent the power dividers. And with this glass-based solution, the amount of added insertion loss that we have with these power dividers is less than around 1 dB or so when you go to these 4-way power dividers, which once again is quite attractive. Now, I mentioned earlier about energy efficiency, and one of the things when you try to go after IoT types of things is that you have to find a way to self-power some of these devices. So we've been working on energy harvesting as well, and this is an example of doing energy harvesting in this 5G NR frequency range from around 24 gigahertz to around 40 gigahertz or so. And if you look at this glass-based solution, the amounts of efficiencies we have been able to achieve with this for RF to DC conversion has been anywhere between around 18 to around 23% or so. Once again, quite good. And if you look at these solutions here, you know, we have two separate implementations to cover two frequency bands. They can be combined together using a diplexer at the front end. So you have a single solution now that covers the entire frequency range from 24 to 40 gigahertz. Now, I mentioned earlier that the package loss is very, very critical. And remember, we have between 1 to 2 dB of budget in terms of the amount of loss that we can allow. So let's look at the package part and focus on the interconnect loss. Now, what this graph basically shows is the comparison of the insertion loss for various different materials that people have made use of, some by us, some that is available in the open literature for different kinds of designs. For example, CPW, microstrip, CPW with conductor backing, and so on and so forth. Now, if you follow all of these over a broad frequency range up to around 160 gigahertz or so, you find that there are materials available that is able to support a fairly low insertion loss. So as an example, if I cover the 5G NR frequency range from around 24 to 40 gigahertz or so, your loss is less than 0.1 dB per millimeter. If you go, let's say, to E band, it's between 0.1 to 0.2 dB per millimeter. You go to D band, 140 gigahertz, it's between 0.2 to 0.5 dB per millimeter. So this is pretty good. The question is, what kind of a package construction are you going to make use of to be able to make use of these kinds of low interconnect loss to be able to create the kinds of solutions you're looking for? So as an example, let's say you're looking at an RF front end and you want to build a diplexer. So in the case of a diplexer, you're trying to cover a fairly broad frequency range, while at the same time separating these two frequencies from an interference standpoint. And that is what is illustrated over here. So you can build these diplexers either by using these hairpin types of filters or edge coupled filters. The frequency response is indicated here. So you see S21. So this is one of the filters, and this is the second filter here. And you see a fair amount of rejection between the two. So these are things we've been able to demonstrate on using a glass-based solution where the thickness of the glass is roughly around 100 microns or so with polymer layers on either side. And when you look at RF front ends, right, you also want to be able to build, for example, your couplers, especially when you have, let's say, an antenna array that is radiating out. And in this particular case, we were able to combine the diplexer with the coupler using this glass-based solution with a 200 micron thick glass with polymer layers on either side. And one of the things we always do when we look at these kinds of solutions is the EVM, the amount of error that you incur due to, let's say, the group delay or the group velocity associated with the signals passing, let's say, through these diplexers. And that is one of the things we have looked at. So if you look at this path here, so you have one direct path, okay, going from the RF source to the antenna. The other one is a reference, okay, coming out of this coupler over here. And the idea is to be able to compare these two kinds of RF power to try and see how much of distortion you actually get. And that is what is indicated over here. So if you look at, for example, 64 QAM, covering a frequency range which is in the 5G millimeter wave range between around 24 to around 32 gigahertz or so, the amount of distortion that we get because of this group delay that you have inside of those diplexers is roughly around less than 5.6% or so, less than what is actually allowed. And this table provides a comparison or a listing of the various filters and the diplexers that we have designed, simulated and measured so far. And the key takeaway from the slide is that all these diplexers and couplers tend to be extremely small, especially when you get into this millimeter frequency range, which is really your 24 to 40 gigahertz range for 5G. Let me now switch gears a little bit into a higher frequency. So this is D band. So now I'm going to 140 gigahertz. And you begin to realize that along with your microstrip and the CPW that I showed you earlier, you probably want to build waveguides as well. Okay, there are different types of waveguides that we are building. One example is the substrate integrated waveguide, but you can work with other kinds or forms of waveguide as well. So this is work that is ongoing that I'm not going to share today, but what I will do is to share some results on the substrate integrated waveguide. And the whole idea here is instead of allowing your signals to propagate through these dielectric materials, why not have it propagate directly through glass? So if you look at this construction here, it is constructed in such a way that you're creating a waveguide where the waveguide is basically filled with this glass material with this polymer on either side with metallization on the top and metallization on the bottom. So this is an example of a rectangular waveguide. And that is what is shown here. So the key thing here is you have to be able to construct these vias going through glass that does not have too much of a taper associated with it. And you want some level of insulation over here to make sure that the reliability of these vias are quite good. And if you look at the substrate integrated waveguide, you're guiding the energy from the left side to the right-hand side, similar to what is indicated here. And to be able to do that, you need to construct these transitions. So this is an example of a CPW feed going into an SIW through this transition that has been designed to ensure that you have good matching as you go from one mode to the other. Now the results of what we've been able to come up with is indicated here. So the dashed line is your simulated results. The solid line represents the measured results for glass-based solution. And this has been compared with LCP as well as silicon. LCP is something that we did a few years back. And silicon here represents high resistivity silicon. Okay, it is not CMOS grade silicon. And you notice that in this particular case, you're looking at a loss of roughly around 0.5 dB or so per millimeter at around 140 gigahertz. Now, what was recently reported by Nokia is this radio on glass module in D-band at 140 gigahertz. And this is quite interesting. So what is shown here is a linear array consisting of 128 elements where these antenna patches, the antenna elements were not patches, but basically slot antennas indicated over here. And what they were trying to make use of was this WR6 waveguide interface to be able to pump energy into these antennas. So this is a 16 slot antenna array. So where 16 slots are along each one of these columns. Now what they were able to demonstrate is that you can indeed achieve an antenna gain of roughly around 24 dBi or so. And you can also do beam steering shown over here. So this is a very exciting result. Now the glass being used over here is a little bit different compared to the glass solutions that I showed you earlier. So this is photo glass with no wiring on either side. So assuming you want to build a 2D array, then you probably want to make some changes to this kind of a solution so that you have enough wiring layers on either side of glass to be able to embed all of the electronics beneath that antenna array. So with that, let me get into 3D integration. And this is a figure that I showed you before. The question is, how can you make this happen? How do you ensure that you're able to create this vertical stack that allows you to have this antenna array on the top side, all these passive phase shifters right beneath it, and the chip beneath that as well, to be able to come up with a construction such that the amount of loss that you incur going from the chip to the antenna is 1 dB or less. So the key takeaway here is that chip embedding is a key enabler. Unless you can find a way to embed these chips, making something like this happen becomes very difficult. In addition to that, when you work with these chips, right, they come from different processes. This is where heterogeneous integration becomes very important because you're using a CMOS die for your beamformer. You're making use of an indium phosphide die for your PA and so on and so forth. And these can come with different die thicknesses, right? And you also want to make sure that you have seamless continuation of the chip wiring to minimize the parasitics. So if you look at the solutions indicated here from Intel, TSMC, this is, I believe the info process, and this is the process from Infineon and IZM. They all show ways by which you can embed the die and create wiring on, let's say, the top side so that you can seamlessly continue the chip wiring to minimize the parasitics into the package with the antennas on the top side, right? But another very important requirement is that you have to get the heat out. And the amount of heat flux that you need to support is anywhere between 75 to 200 watts per centimeter squared. The number goes up as you go up in frequency. And not only do you have to remove the heat from the bottom side, you probably want to remove heat from the top side as well if you assemble chips over here. So this is one of the areas we are focusing on quite a bit. And the solution that we are trying to go after is indicated here, where we are making use of these embedded chips inside of these cavities in glass with wiring layers on top. The antenna sits here, the passives would sit over here, and then trying to expose the bottom side of the chip to be able to attach these heat spreaders to make sure that you can remove the heat from the bottom side. So I'll try to cover some aspects of that shortly. So let us look at this construction itself. Let me start by looking at the assembly loss. So there are two fundamental ways by which you can assemble the chip onto a substrate. One is wire bond. Even to this day, the RF community makes use of this quite a bit because you can always design these transitions such that you can absorb the wire bond loss into the overall solution that you go after. The second is a flip chip solution that all of us are familiar with. The third is what I was trying to show you. If you can completely eliminate that wire bond as well as this bump, the solder ball over here, you can directly have these microvias making contact with these chips that are embedded in the substrate. And notice, as I mentioned earlier, the thickness of the CMOS die can be different compared to the thickness of the PA die. So you have to somehow create these cavities in glass that has different thicknesses associated with them. And if you look at these microvias, they give you an insertion loss of roughly around 0.15 dB at 140 gigahertz. And if you compare it with, let's say, wire bond or flip chip, you're doing much better. So it's around 0.15 dB lower than flip chip and around 1.65 dB lower than wire bond. The reason I show that is every single building block that you make use of to be able to connect that chip to that antenna contributes towards that 1 dB of insertion loss budget, overall budget that we have for the package. So with that, let me try to take you through this chip first and chip last assembly. So what we have been trying to do is to minimize this vertical distance between the IC and the antenna. And you can do that in multiple ways. So you can create these cavities in glass. You can have multiple dies in a single cavity or single die in each cavity. And by having a single die in each cavity, you can make use of glass material as an insulator to be able to, as a thermal insulator, to thermally insulate one die from the other. For example, the CMOS die from the PA die. Now, if you embed two dies into a single cavity, then you can connect the two through this wire, where the length of this wire can be 100 microns or less. Now, assuming you assemble a die on the top surface, the length of this interconnect can be as short as around 100 microns or so. So you can basically reduce the overall insertion loss going from the die to the chip that is assembled on the top. And as I mentioned to you earlier, the insertion loss of a single via is roughly around 0.15 dB or so. The construction that we have based on this glass-based solution is a little bit different compared to what has been done in the past, either by using this SiFO process from Infineon or the TSMC Info process that makes use of an epoxy mold material. In this particular case, there is no mold material that we make use of. So here are some recent results. So this is an example of where we've been able to embed 2 dies in one cavity, 4 dies in one cavity, single die in a cavity, right? And not only that, we are able to expose the bottom side of the die and cover it with silver epoxy material that works as a thermal interface material. And if you look at the cross section here, there's an example of a 300 micron thick glass, and that is your IC that has been embedded with a thickness of around 300 microns. And if you look at the die shift that we have, it's roughly around 2 microns. There is no assembly, as I mentioned earlier, and you can come up with a double-sided solution. So now think of your CMOS die and your indium phosphide PA that need to be connected to each other, where each one of these are in separate cavities. And the length of this line, let's say, is around 500 microns. It's a CPW connection. Notice that at 140 gigahertz, the amount of loss that we incur is slightly larger than around half a dB or so. So with that, let me come to thermal management. Now, I mentioned earlier that you have to find ways by which you can remove the heat from the bottom side of the chip, especially when you are embedding chips, because this PA chip and these CMOS beamformer chips can run extremely hot. Now, one of the ways by doing that is by making use of thermal vias, similar to what is shown over here. And in my opinion, these thermal vias, they completely defeat integration because they increase the thermal resistance. So what you want to do is to find ways by which you can expose the bottom side of the die and connect this heat spreader directly to the die to be able to get the heat out. And you can certainly do that, up to a heat flux of around maybe 150 watts per centimeter squared or so. But beyond that, you need something a lot more because the size of this heat spreader tends to increase quite a bit, as you go past this heat flux. And that's where we believe vapor chamber based solutions becomes very, very attractive. If you want to get to heat fluxes larger than 150 watts per centimeter squared, where these vapor chambers indicated here above this cold plate can be made extremely small. One very, very important takeaway here is that you need very good thermal interface materials that are ultra thin, that have very high conductivity to be able to connect this copper heat spreader to the bottom side of the die. So you see the silver epoxy material has a thermal conductivity of between around 25 to 30 watts per meter Kelvin or so, and that becomes a major showstopper. So what we are doing at PRC is to develop some new materials that has a much higher thermal conductivity compared to silver epoxy, while at the same time has a CTE very close to that of silicon, so that the reliability can be increased quite a bit.
Professor,
yeah.
Apologies for the interruption. You just have about 10 minutes left, if that's okay.
Yeah, let me try to conclude in 5 minutes. Is that okay?
Yes, and then maybe we might be able to have some questions.
Sure, absolutely. So let me very briefly touch on millimeter wave design, and then I'm going to try and stop. So all of us working in the design area know how difficult and how complex it becomes when you're trying to design these very complex solutions. So here is an example that I show on the right-hand side where we are flexing glass. So these are for flexible electronics applications by using very thin glass down to around 30 microns or so with metallization on either side. So when you're trying to do something like this, all these multi-physics interactions become very important, and therefore the solution process itself becomes extremely complex. And you need to make use of some other ways by which you can solve or address these kinds of design related issues. And we believe machine learning play a very, very important role here. So I'm going to very quickly go through this. So we've been spending a lot of time on predictive modeling, where, for example, if you take a hairpin filter design that I showed you earlier, you can make use of machine learning to spit out designs almost with seamless, with absolutely no effort at all once you have trained these kinds of models. You can also do inverse design, where given the kind of performance you're looking for, you can go backwards and try to figure out what should be the design of, let's say, the substrate integrated waveguide. And the reason why this is so important is that you can come up with solutions that you probably did not expect before. And that is what is illustrated here. These two candidate solutions shown here, one is something that we expected. The other is something we did not expect, and that came about as a result of this invertible neural networks. So they become very useful when you're trying to get into design space exploration. Similarly, when you get into optimization, which is a very, very important part of millimeter wave design, you can get into all kinds of issues because at very high frequencies, let's say D-band, 140 gigahertz, you are relying on EM simulations to be able to come up with the solutions. And for example, if you look at this air cavity filled substrate integrated waveguide, there are several parameters that you're trying to tune. In this particular case, 14 parameters. And you'll find that if you are trying to reach the optimum solution, very quickly a lot of the optimization-based algorithms will fall apart, especially when the dimensionality of the problem increases. So we've been spending a lot of time in this area, making use of these active learning techniques by making use of some unique kernels, unique tree-based approaches. But what is the key takeaway here is that by making use of these approaches, you end up with solutions that are roughly between 30 to 35% better as compared to other optimization-based approaches. And all this is based on machine learning once again. So with that, I'm going to conclude with just a couple of slides here. So what do we do moving forward? Now, we all, I'm sure, agree at this point in time that we are entering this data-centric era, okay, right here, where 5G and beyond, what we call as 6G, is going to play a very, very important role. We also know that heterogeneous integration becomes very important. Now, when you bring intelligence into the mix, you probably want to have some kind of a wireless solution at the front end that allows you to interact with the environment, and some level of compute at the back end that has a lot of artificial intelligence associated solutions associated with it. So when you're coming up with a construction like this, you are probably moving data over long distances using wireless communication, let's say greater than 100 meters, but you also need to move data over shorter distances using this computer processing over a distance of less than 100 meters. And that basically means that you need to bring together different technologies like wireless, compute, photonics, sensing, and so on and so forth, but also with high energy efficiency. That becomes a very, very key requirement. And that is really our vision at the PRC. So what we believe is going to happen in the future are these very advanced interposer solutions where you have the wireless interconnect such as the antenna integrated on the interposer that needs to coexist with a lot of the compute-based processing solutions such as the CPUs, the GPUs, the IVRs, and so on and so forth, including the 3D stacks. Also, these photonic ICs, because bringing photonic IOs into that package becomes very, very critical. And an embodiment of the solution is what is indicated here. The key takeaway here is if you're trying to look at emerging applications in the AI, automotive, wireless, and the space area, you need a holistic approach that brings together the various elements that are indicated over here. So with that, let me just summarize very quickly. Okay. So wireless communication in millimeter wave offers several opportunities. I think we all agree to that. No issues at all. But what is a key takeaway from this presentation is that advanced packaging is a key technology enabler. I covered some of these areas here. And ultimately, wireless integration is just part of the puzzle. You need to bring other kinds of interconnect solutions or packaging solutions as well into this heterogeneous integration platform. So with that, let me stop here. Thank you so much for joining this presentation. I just want to acknowledge 3 other centers, Ascent, ComCenter, and Camel. With that, let me stop here. And if you have any questions, I'll be very, very happy to answer. Thank you so much.
And thank you so much, Professor Swaminathan. I think an excellent update on a lot of the packaging developments that are being driven by 5G and higher frequency applications and challenges. We did have one question so far. Can we build a standard test coupon for characterization of different variables, for example, different materials for build-up, etc.?
The answer is absolutely yes, and that is what we've been doing. And this is also being done through this task force that is part of the iNEMI initiative, where different materials can be looked at, different kinds of stack-ups can be looked at, compared. And what we've been doing here at PRC is to cover a fairly broad frequency range. At this point in time, we go up to around 170, but we do have the capability to go far beyond that as well.
Great, thank you very much. And thank you for highlighting the work that's ongoing by that particular project, which I think is a very good cross-industry effort on what obviously, you know, is a pain point for everyone. In terms, would 1 or 2 other questions come in? What glass electric properties matter most for antenna on glass?
Sure. So there are several issues you need to think about, right? So one is, of course, you know, the glass has to have a low permittivity. If you're trying to have antennas directly on glass, we know that antennas tend to radiate better if you're trying to make use of a lower dielectric constant material between that, let's say, the patch antenna and the ground plane. So the permittivity of that material becomes very, very critical. And of course, it's loss tangent as well. Now, in addition to that, realize that you have to be able to feed these antennas. The question is, how are you going to feed it? If you're making use of a linear array, you're just making use of horizontal lines or lateral lines to be able to feed it. If it is more of an area array or a 2D array, you're feeding it vertically upwards. So once again, the feed mechanism that you make use of is going to dictate what kind of properties you need for that glass material.
Great, thank you. And then I think we can finish with one more question before we conclude, and that's what measurements are needed to support 3D integration?
There are different kinds of measurements that one needs to have. So on the electrical side, I took you through several of these. For example, if you're trying to build antennas, you want to measure the return loss of the antenna. You want to be able to measure the radiation pattern of the antenna, including the efficiency and so on and so forth. You also want to characterize every one of the building blocks that you have. I showed you some examples of, let's say, trying to figure out what is that interconnect loss associated with these kinds of structures that you're building, and so on and so forth. In addition to that, there are other issues that you need to tackle as well. And one of them is if you're trying to build, for example, these polymer layers on top of glass, you want to make sure that the adhesion of copper to that polymer material is as good as possible. So you have to go through a set of tests to make sure that that is possible. So that translates into the kind of reliability you can expect from a solution like this. Then from the thermal side, you probably want to make use of these heater chips to be able to make measurements to ensure that indeed you can get heat out of these modules, right? And things of that nature. These are just a few examples, but unless you have a set of measurements or sequence of measurements you go through on a continuous basis, you will never be able to construct and realize a technology like this.
Thank you very much. And again, just as a reminder to everyone, the presentation, we will send an email out to everyone who attended today, and you'll have an opportunity to get a copy of the slides and access to the recording as well. So with that, I'd like to thank Professor Swaminathan from Georgia Tech for a very interesting seminar today, and a great kickoff, I think, to the iNEMI 5G webinar series that we're going to be running over the next number of months, and highlighting some of the, I think, the key developments across the industry in this area, and some of the key challenges that we're facing on, as we talked about here, materials, packaging technologies, measurement methodologies. Urmi, would you like to add anything here?
No, thank you very much again, Swami. I see Robin online. Hi, Robin. It's been a long time. Thank you again. And thanks everybody for your participation, and look forward to having more interactions. If anyone's interested in the iNEMI program, you can look up on the website, the one that Professor Swami also mentioned. In addition to that, of course, there's a lot of very, very interesting work going on in the PRC that you already heard of, and it's really progressing great. Thanks again, Swami. Looking forward to working with you. Thank you.
Thank you so much. Thank you all. Take care.
Bye.
Yes,
Bye.
Thank you all, everyone. And just a reminder, the next webinar will be on April the 8th. And it will be from Professor Michael Lanigan of Penn State. It'll be on broadband dielectric characterization of polymers and ceramics in the 5G frequency range. So hope you'll be able to join us for that or other future ones in the series. Thank you again to everyone, and goodbye.
Bye.
Take care. Bye-bye.